Okay, yeah, sorry for the delay there. Yeah, I'm gonna talk about the EVM object format, and I wasn't sure, who's the audience, and so I kind of like left a mix of different level of depth. But first, I was really happy yesterday when I found this, because this was the first time I found in the original wiki what is the design goal of the EVM. Yet I worked on it for like, I don't know, 6 years at this point or 7. And it's quite funny that the original design goals were kind of on spot. We actually did achieve most of these goals. And I want to highlight one. The first one here is simplicity. We definitely achieved that, but maybe we have overdone it a tiny bit, and it's biting back now. And if I would have been there writing this wiki, I would have added 2 more design goals. I would have added a design goal to be extensible, so that we can add and remove features without disturbing existing stuff. And I would also have added validation, so that there's no code which looks invalid enters the state. But we didn't have these goals, we didn't have any of this, so here we are now. And I just want to introduce like 4 different issues we have identified, and we are kind of like solving these issues with the EOF. So the first issue is we have all kinds of instructions. Basically, any kind of byte can exist in the state, and it can map to any kind of instruction. We have all these bytes which do not map to an instruction today. And if we introduce a new opcode which tries to take up that byte, then suddenly we have contracts which change behavior. So it's kind of really messy to introduce features because anything could happen. The second big issue is basically data bytes and how they interact with jumps. So we have, for one example, we have the single instruction called push, which takes an immediate. No other instruction takes an immediate today. And we do not want to execute any data which is part of this immediate, because that would mean that we can have like self-modifying code and code which does weird things. How do we prevent this? We prevent this by not being able to jump into the push data. And that's the reason we have this jump dest byte as well. And validating this at runtime is kind of sketchy, and we don't do that. Therefore, we have this process called jump dest analysis, which is done before execution. And this cannot be done from any point of the code. It has to be done from the beginning. And it's done at every single time the code is executed. Now, some clients do some kind of caching, but it's not generally part of the specification. We also have data sections. Think about init code. When we deploy a contract, there's an init code, which then has the actual runtime code at the very end, which is returned and then stored in the state. But of course, besides that, practically 99% of the deployed code is compiled from Solidity, and Solidity has this metadata at the end, which is just some random data. And the main issue with this data is we don't want to jump into it. We want to have separation between the two. And technically, if there's like a jump dest and the method, like this data section is properly formatted, we could actually jump there, and we definitely break the separation of code and data. And in many cases, especially the case of init code, the init code would be small, but the data, the runtime code, would be big, and we run this jump dest analysis on this entire blob, which is unneeded. And of course, the last dreaded issue is removing instructions or like deprecating them, not allowing new code to use that. That is just not possible at all today. As you can tell, EOF is a solution to all of these and many other things. The main goals we have is to separate code and data, have some kind of a validation process, and to be also extensible. Now, I mentioned versioning here, but it may not need versioning to be extensible. EOF itself is a set of different EIPs. The first 2 EIPs here are the core of it, and those are kind of accepted or, I don't know, considered for Shanghai. We're going to see when Shanghai is going to come, first of all, and whether these going to make it. But the first 2 look like that they're going to be in Shanghai. I kind of hope that this third one, static relative jumps, would also make it. I'm not hopeful that the function stuff going to make it. That's too complex. But the static relative jumps is really interesting. Now, the first EIP itself just defines the structure and some basic validation. This is how the EOF bytecode going to look like? We have a header at the top, which starts with like a magic, a version, and then you have the actual sections, which is just the section headers. You don't have the content there. So you have the section headers, you have a terminator, and then you have the actual content. Now, to visualize this, here's like a legacy code. Of course, the space here, it doesn't matter, it's just a space. You can put spaces into hexadecimals. Don't be concerned by that. But if you compare the legacy code against the EOF, you can notice that there's like this header. That's the header I described before. Now, to dig into what this header looks like, of course, we have the magic, we have the version. It is the first section, which describes the code. It sets the length of the code. The second section is the data, which also just describes the length of the data. There can be EOF bytecode which doesn't have data. It can be only code, or code-only bytecode, but there can be bytecode which has code and data. And lastly, we terminate the header, and then we have the actual code. Now, this example is like an init coding sample, a contract creation code. This is pretty standard. It just returns what is the runtime code, which in our case is this one at the end. It doesn't do anything. Now, apart from having like this structure, we also have to change EVM semantics a tiny bit. And the only things we change is basically around control flow. Control flow instructions like jumps, BC, etc. They have to be limited to the code section. They cannot go outside of the code section. But we still need to keep code copy and all these things intact, because we want to be able to copy the data here. So if you look at this code example, code copy basically reads the entire container and just returns the data section. Now, since we have these headers, we also want to validate that these headers are are correct, and we're not just taking anything which looks like an EOF header. So we have some kind of a validation procedure at the time of deploying code. And this process is kind of flexible as well, because we can have legacy code. Legacy code obviously is unaffected. It can continue deploying legacy code, but it could also deploy EOF code. And the same happens with the EOF code. This is actually one of the topics we could discuss at the workshop, whether we should have this case of EOF deploying legacy code. These things are flexible. It's really important to mention that, if we have this validation, that we make sure that EOF code in this state is valid, the question arises, okay, what happens with code which has been deployed prior to Shanghai? Can there be code which looks like EOF but never has been validated? And that is a really valid question, and the answer to that is no. And the way we solve that is through this magic. Which is magic, of course. Now, in London, we have deployed a previous EIP. We just rejected this EOF byte to be the starting byte of a bytecode. And we were kind of hopeful that nobody going to deploy before activating that EIP. Nobody going to deploy any code which starts with EF. But of course, 3 people did. And so we cannot go with the EF, single EF magic byte. But this is by design. That was the reason for this EIP, right? It just kind of said that these people did it. But anyway, we can still go with EF00, 2 bytes for a magic. And the reason we choose 0 because that's cheaper in call data gas. So basically, this magic prevents that in the state currently, there's no code starting with the EF00 byte. So whenever we deploy an EOF validated code, we can be sure that that is validated. And this magic, actually, we compared not only on mainnet, but we looked at most of the useful, it's most of the useful L2s and testnets, and none of them really have any code starting with EF00. Now, moving on to the next EIP, the code validation, which is an extension on top of this. And it is pretty simple. The reason we separated these two, because we weren't sure, that even EOF would be accepted, and then code validation, so we just separated it, but it seems like you guys like it. Code validation is an extensible system. The first 3 steps we do in it that we don't allow all of these random instructions to be deployed. So when you deploy an EOF contract, it won't have opcodes which are not assigned to anything. We also want to prevent having truncated bytecode. so there won't be push data at the very end, which is truncated. This actually helps some optimizations in interpreters. And we also want to make bytecode properly terminated with stuff like stop, return, revert, etc. This also helps interpreters. And lastly, we could also use this system to deprecate opcodes. We could say that new bytecode cannot use call data, the call code opcode, or cannot use self-destruct. And now lastly, my, I guess, most favorite EIP out of all of these is the static relative jumps. There has been like a long discussion, all of these dynamic jumps, analyzing bytecode, what is the control flow of it. And it turns out that actually Solidity, like most of the over 95% of the jumps in Solidity code is not dynamic. It is fully static. It just jumps at known locations. The only thing which is dynamic in Solidity is return to caller. Now with static relative jumps, we can actually make these static. We can remove both the jump desk, we can remove the push instructions, we can save space, and we can also save gas because we don't need to do any analysis around it. This is validated at deploy time. So it's pretty awesome. But it also is a building block for other changes, like having functions or having subroutines, or even having like this return to caller on top of this. And EOF itself, we kind of hope that it is a building block and it will enable other features as well. I listed a bunch of features here, subroutines I mentioned. But one issue with like 3074, and I'm sure Matt's going to talk a lot about all of these. One concern people had with 3074 is, OK, how can I, once I give authorization, how can I revoke it? And you could have like a revocation system with EOF, with like a special section in EOF. And lastly, there's also like this really interesting EIP to introduce complete control flow validation at deploy time. That also depends on all of these EIPs I've explained. So I guess that's in short. You can find all of the EIPs, all of these talks, etc., on our website. And I hope that we can discuss all these details on the workshops. Thank you.